Let us take some common industry statements. Companies don't have any money to invest today, but when something breaks down, they have all the money in the world. This is a reactive approach. Companies are often not aware that the problems they have are caused by contaminated oil or lubricant. They don't realize that micron-sized particles can cause devastating damage to their components and systems. This is a lack of knowledge. Companies constantly tell you they don't have a problem, but send expensive pumps, valves, and other components for repair all the time. They also have long lead-time spare parts in-house to avoid downtime when equipment fails. This is a reactive or preventive approach. Companies rely on the oil supplier. The supplier tells them when to change the oil, which is time-based, and even takes a sample, just particles and maybe water. If the oil is very dirty, they recommend changing it, which is preventive. The goal is to move to condition-based, to predictive or proactive maintenance. Oil is a very important component. Oil is still too often seen as a consumable and doesn't receive the attention it deserves and requires. Oil is like blood to a human body. Its cleanliness is essential to the functionality of a system. Without a lubricant, a gearbox would get damaged in no time. And without oil, a hydraulic system doesn't even work. Do you know that new oil is one of the worst sources of particulate contaminant system ingression? Lubricant contamination. Contamination in lubricant is the root cause of premature lubricant degradation and accelerated wear of machine components. Prevention and control of contamination is very often the most reliable means of preventing equipment failure and keeping lubricant dry and clean. The common contaminants are dirt, which are solid contaminants, moisture or water, soot, glycol, air and fuel dilution. Sources of contamination. Dirt or particle contamination could be as a result of the following inbuilt, internally generated, external and poor maintenance practices. Moisture or water contamination. Water exists in lubricating oil as emulsified, dissolved and free. Water is the leading cause of hydraulic pump cavitation, also known as vaporous cavitation. Water encourages aeration problems such as foaming and air entrainment. It also puts bearings at high risk when the machine is at rest. Once static etching or corrosion gets started, bearing failure is imminent. Water ingression is the second most destructive contaminant and can wreak havoc in your system. This could be as a result of the following: pressure or temperature differential, vents or breathers, level oilers and seals, contaminated lubricant, and poor storage or handling practices. Air can exist in oil in 4 different states of coexistence. They include the following: dissolved, not visible, no clouding present, and can represent as much as 10% of the total volume. Entrained, unstable, microscopic air bubbles with clouding present. Free, trapped pockets of air in dead zones, high regions and standpipes. Foam, highly aerated tank and sump fluid surfaces with more than 30% air. The problems associated with aerated oil include oxidation, thermal degradation, poor heat transfer, retarded oil supply and cavitation. Particles are the most harmful form of lubricant contamination. A sample of lubricant may appear to be immaculate, but actually contain many microscopic particles. There are many potential sources of these microscopic particles. During production of the lubricant, raw materials and manufacturing equipment can introduce particles. New or used machinery and reservoirs may contain dirt, metal fines, casting sand, bits of solder, and so on. Particles can enter through apertures, leaks, worn seals, and vents in machinery. Particle contamination can occur when components are replaced or equipment is serviced. Solid particles account for the majority of all failures in an oil system. The most harmful are clearance-size particles of similar size or slightly bigger than the dynamic tolerance between the moving parts in the oil system. Dynamic tolerances in an oil system are extremely fine. When tiny abrasive particles such as sand and dust get into the oil system, they flow with the oil into critical machine components and are wedged in the fine clearances. This leads to microcracks being initiated in the surface of, for example, a ball bearing, and the load and stress cycles will spread subsurface cracks, resulting in degradation of the metal and releasing large spalls. They initiate irreversible microscopic damage that grows into macroscopic damage and can disable and destroy bearings, gears, valves, and other components. Particle contamination can also shorten the life of a lubricant and increase energy consumption. Microscopic particles can scratch or gouge surfaces, removing the metal, which is referred to as abrasive wear. This can occur inside sliding contacts such as gear teeth, pistons, and certain types of bearings and cams. 1. Set cleanliness targets. The target cleanliness level should reflect reliability goals and application-specific requirements. 2. Take specific actions to achieve targets. Reduce ingression. Use secondary filtration, whether permanent, mobile, offline, or online. 3. Monitor oil cleanliness levels consistently. Use oil analysis, particle monitors, and fluid patch test kits. The understanding ISO cleanliness codes. The ISO cleanliness code is used to quantify particulate contamination levels per milliliter of fluid at 3 sizes: 4 microns, 6 microns, and 14 microns. The ISO code is expressed in 3 numbers, for example, 19, 17, 14. Each number represents a contamination level code for the correlating particle size. The code includes all particles of the specified size and larger. It is important to note that each time a code increases, the quantity range of particles is doubling. Establishing a contamination control program. There are 6 basic steps to initiate an effective contamination control program. These are understanding and education, identifying, monitoring, response, removal, and prevention. In this video, we will concentrate on the removal process using the Descase RMF Giant Offline Unit, also called the Giant. If contamination is present in systems and lubricants, an important component of an effective contamination control program is the removal of the foreign material. Different technologies are available for the removal of foreign debris. It is important to select a technology that will be able to remove the type of contaminant present. Particle contamination removal can be accomplished utilizing several different filtration methods. Filtering is one of the more common methods for removal of particle debris. Water contamination can also be removed via several separation methods. The effectiveness of these methods will be dependent on the type and concentration of contamination present. The Giant Offline Unit. The Giant Offline Unit is also known as the Giant. The Giant's filter housing is combined with a pump motor group and an electrical control box. This is an easy-to-use plug-and-play filter solution. It only requires electrical power, suction, and return lines. The Giant Offline Filter Unit can be easily mounted to new and existing hydraulic installations. By means of an integrated pump motor unit in the offline filter, the oil is pumped from the reservoir through the filter unit, and after filtering, the oil is then returned to the tank. If required, elements are available in different micron sizes to suit any application. Water-absorbing elements can also be applied. The RMF system's Giant Offline Filter is especially designed for industrial hydraulic and lubrication systems. The pump is a cast steel low noise gear pump with a large viscosity range from 12 centistokes to 800 centistokes. Delta P indicator is standard in the delivery. A range of filter elements is available for the Giant, running from 1 up to 25 micron. The filter elements have the capacity to remove even the smallest of dirt particles from the oil. When fitted with water-absorbing elements, the reduced water contamination level prolongs the life of the additive package and reduces oxidation of the oil components and bearing surfaces. Monitoring. The Giant can be equipped with additional components for condition monitoring, such as the CMS, which stands for Contamination Monitoring System, the OQS, or Oil Quality Sensor, and the OQD, the Oil Quality Display. The electrical control box is already prepared for these additions. The CMS can report oil cleanliness levels in all international standard formats, including 8-channel sensor sizes from 4 to 70 micrometers. If required, the CMS can include the optional moisture and temperature sensor to report water content in relative humidity percentage. Applications. The Giant can be used on hydraulic power units, lube and oil tanks, large gearboxes and storage tanks for biodegradable fluids. Industries that are successfully applying the Giant include the steel industry, marine industry, automotive industry, and the pulp and paper industry. System contamination. In the hydraulic market, it is an accepted fact that contamination causes 80% of all mechanical failures. This contamination results from the presence of solid particles such as metal, sand, and rubber in oil. Water contamination can cause corrosion, metal surface fatigue, fluid breakdown, and reduced lubricating film thickness. To protect your machinery and ensure optimal performance, take action now. Implement a robust contamination control program today. For more on contamination control, visit www.dis-case.com. For more updates on machine condition monitoring, please visit www.monitormaxengine.com and follow us on YouTube at MonitorMax. Like, comment, and share.